need like 5 different dictionaries to translate what I'm looking at.
Well, now we're about to do some philosophy right here. That makes me nervous.
Oh, that thing, the nomenclature.
Coordination.
Yeah, that's just information. I'm not going to hold you to that. Okay.
Cobaltate.
Let's move it over like this. Go. Okay. Already recording.
This is it.
It's a short one. Yep.
Don't be fooled. Feel how thick this is. Don't be fooled, okay? Just
I'm trying to load you into a false sense of security.
Look at all the numbers. Oh God, it's all that.
yeah, see?
There's like 100 questions here. Oh.
Okay. So, unmute. Where is it? Here it is. This one. Okay. So, like I mentioned before, once we dip our toes into equilibrium, kind of stuck there for a while. So, now we're going to deal with equilibrium in terms of solubility of solids. And these are going to be aqueous solutions. Keep it simple. And the equilibria that are the equilibrium, yes, that describe complex ions. A useful way to think of solubility versus complex ions is solubility, you start with a solid and you end up with usually 2 things in aqueous solution. That's it. Whereas complex ions, you start off with a solid and you associate it with some, not a complex ion, but with some ligand that you can find in this nomenclature.
Doctor, can you move that to that?
Oh, okay.
That's what
Like this?
we do.
Okay. Okay, we're good. And this forms a soluble form of the solid. Okay, in aqueous solution, but it's not a well, it is an ion, so it could be positive or it could be negative. All right, that's just a rough introduction. Let's get into the meat and maybe it'll make more sense. Because that didn't work out as well as I thought it would. Okay, so in terms of solubility, remember when I drew this distinction between the equilibrium constant and the equilibrium position. Those are 2 separate ideas. The equilibrium constant for a given temperature is always the same, never changes. But the equilibrium position actually is an expression of Le Chatelier's principle. Because if you're at equilibrium and you say, add some product, it's going to shift back. to reactants, right? But it won't use all of it up. In other words, the concentrations will change in equilibrium position. But at equilibrium, all of those concentrations together in the form of K, still the same. Okay? So let's take that concept and apply it to solubility. When we talk about solubility product, say we have a okay, so Le Chatelier's principle, one of the first things we did was we had a saturated solution of sodium chloride, right? Okay. So there you have sodium chloride solid, and it's in equilibrium with these two ions in solution, just like that. Okay? The solubility product is just an expression of that equilibrium, right? So it would be a K, and if we, let's see, for argument's sake, let's just write the whole thing out. Of course, we know by convention that that term goes away, right, because it's a solid. So that's why we call it the solubility product, because all expressions, equilibrium expressions for the solubility of a solid are a product, because the reactant side is the solid, which would normally appear in the denominator, but doesn't because it's a solid. So it's always a product. That times that equals this. That's where the solubility product name comes from.
As in, it's not ever NaCl plus something else. So it's just working with individual ions.
Right. Whatever this dissociates into to become soluble.
So basically, we're saying bond number out.
Yes. That's what we're doing. For this expression, of course, it's a little more complicated, right? We only have a coefficient of 1 and 1, so that the exponents here are 1 and 1. But for something like this, bismuth sulfide, you get 2 bismuth ions and 3 sulfide ions. So you still get the powers.
So, what's bismuth? Oh, I see.
Here. Have you ever taken Pepto-Bismol? Look on the label. Pepto-Bismol is bismuth subsalicylate. It's a salicylic acid derivative of bismuth.
Wait, it's acidic. Interesting.
Not necessarily, because you've got this cation in there with it. Yeah, if it were salicylic acid, pure salicylic acid, it would be acidic, definitely. Right?
So it probably wouldn't be as effective or advertising for.
Right, it would be something, you know, yeah, it would have a different physiological effect. Right.
I was just looking for bismuth on the chart. It's
Oh,
83.
right.
It took me quite a while to find this. Because I was like, just looking for, I usually look at the top first, because that's where we usually work.
Yeah, it's normally not something that you deal with. Okay, so the solubility product expression then has to include here the coefficients, just like any other equilibrium constant.
So how do you read that? You say the KSP, do you just say that's the solubility product, or do you say
Yes.
the constant solubility?
It's usually referred to as solubility product.
But we know that we're calculating an equilibrium constant.
That's true.
Okay.
Right. They're synonymous. And this is the expression. Of course, there's a solid, so these are the only two terms that enter in.
So is that
That's this part.
sulfate?
I'm sorry?
Is that bismuth sulfate?
Sulfide.
Sulfide.
Mm-hmm.
Sulfide.
Yeah. And let me see. Bismuth, does it have any other? Okay, bismuth could be a +5 or a +3. So we would have to say bismuth 3 sulfide.
Right. Last semester. Took me a second to look.
Can't let you forget it. Then there's the equilibrium position, which we designate as solubility. And with reference to solubility products being an equilibrium constant and solubility being an equilibrium position, solubility references how much of this dissolves in aqueous solution. That is, what is its molar concentration? Okay, we're going to do some calculations.
So it can be assumed it's a maximum of 40, isn't it?
Huh?
I said we can assume it's not going to be above 40, right? Since the molarity of the water is 40, isn't it?
Oh, yeah. Well, yeah, technically speaking. Actually, though, some things can't be more soluble.
That's just because they're so small, the way they interact.
Well, no. As you add more of the solute, the concentration of the solvent goes down. So it doesn't stay 40 all the time. So as you add more, it's like making sugar water. So you add sugar, concentration of the water goes down as the sugar goes up. Eventually, you reach a point where there's more sugar than there is water. Right. But usually, these solubilities are going to be small numbers. Okay. So if we have several salts at a given temperature, and we have a list of K values. So say K of this one is greater than K of this one is greater than K of this one. Just for argument's sake, we have 3 different salts, and we compare their K values. Does this automatically mean that their solubilities, this one's solubility is greater than that one, is greater than that one?
You know, I can logic my way to think that the answer is no.
Right.
Not necessarily, but I'm not
And
sure
then-
if I could explain why.
Okay.
But because one is just a simple.
What does the solubility mean? Remember that. It means how much of this one goes into solution.
Right, but that
Right.
doesn't necessarily seem like it would be dependent on what the constant is, like the solubility product.
They're related.
But it
Yes,
doesn't seem like
but-
it would be 100% dependent on their
No.
solubility depending on it.
The trick is the coefficients, right? Because this expression is that one to the x and this one to the y, but the solubility depends only on the temperature, how much goes into solution. So the K is going to be influenced by the stoichiometry. So if you have large coefficient values like 2, 3, 4, 5 here, that's going to throw this K. It's going to make the K huge. But if this one had that doesn't mean the solubility is going to be huge. I think we need an example. Solubility, actually, this is not entirely true. Solubility, yes, is often expressed as how many grams of the solid will go into solution in 1 liter.
Later.
But, yeah, but very often you'll see it expressed as molarity too.
So
So molar
solubility
concentration.
is a number we can calculate.
Solubility? Yes, we can calculate it. We are going to.
That's relatively bizarre.
I think it'll make more sense once we start doing some problems. So let's take this one. Silver chloride and water. That's a good example. Silver chloride is, we learned last semester that silver and chlorine on our little chart, when they cross, you have a gray box, right? Insoluble. Fact of the matter is, it's slightly soluble. You know, it's not completely soluble, but some of it does dissolve in water. Only a very small amount. So there's your KSP. So let's write silver chloride becomes this in solution. And then the solubility product is equal to 10 to the minus 10th. And that equals the equilibrium concentration of that one times the equilibrium concentration of this one. Okay. Come on. Here we go. So there's our, well, that's supposed to be a double barb arrow. So there's our equilibrium expression. Now, why did we pick X? Let's do it this way. Hold on a second. Let me move this out of the way. Let me see if we can do this using an ice table. This one's not going to have any terms in it, right? Because it's not part of the equilibrium. Right? So we're only focused on this side. When we start out, that's 0, right? Right? We just put it in the water. Nothing's happened yet. But yeah, that's true. Yeah. So what's going to happen? Well, as some of this dissolves in that, we get some of that, right? An equal amount of that because it's 1 to 1. Okay, so far so good? So we end up with this and that as our final. Now, here's where you draw the relationship, the connection between solubility product and solubility. Solubility says, if this is X, then this amount of X, of course, in molarity, will be the solubility of this, because it's 1 to 1. Right? So if we can say X molar silver, then we know that's so many moles of this went into solution to produce that one, because it's 1 to 1. That's why we're saying here that X is the term for solubility. I can tell it hadn't sunk in yet. Okay,
So we have a molar concentration for silver and chlorine. The 1.3
Right.
times 10 to the negative 5.
This means, since this is 1 to 1, and that, this would be like, you know, that many produce that, but it's not part of the expression, right?
So how do you, I'm just like, language-wise, then what are we saying? We're saying that the solubility of silver chloride in water is 1.3 times 10 to the negative 5
Molar, yes.
molar.
That's exactly what we're saying.
saying it as silver chloride. We're not saying the solubility of silver or the solubility of chlorine. We're saying it as a molecule of silver chloride.
Yes, and we can say that because of the stoichiometry. That X,
Just because it was 1-to-1, we say
Yes.
it like that.
we can say that.
So do we have an example where it's not 1-to-1?
Yes, we will have.
Probably
Maybe the next one.
like
Well, let's do the next one.
let's say calcium and sodium or calcium.
We're going to do silver phosphate next. So we need to write what silver phosphate is. Silver is +1. Phosphate is 3-, right? So we need 3 of those. That gives us,
So phosphorus is 3-.
yes,
So we're going to use, I don't want to look. I want to see if I can figure this out with not looking at the board.
okay.
So the first thing we do, and I'm not looking at the board, is to separate the silver and the phosphorus. But to balance it, we need 3 silvers.
Mhm. Yep.
But where does that go? So is it Ag3P?
No, silver is a separate cation. Phosphate is a separate anion.
And this is
Oh, phosphate. I was just writing phosphorus. I didn't write the oxygen. Oops.
just a very, very small percentage of silver and chlorine that are associated. Most of it's still silver chloride, right?
Yes, for this one,
Mhm.
that is definitely true. Yeah.
So okay, I wrote phosphorus, not phosphate. That was where I messed up. Okay. So then we have a coefficient of 3 in front of the silver and PO4.
Okay. So you have a balanced equation yet?
Yeah.
Okay. So now, the key here is to pick your X so that it represents the solubility of the solid, right? So there's 1 here. There's 1 here. So let's pick this one. Well, of course, it's going to start out at 0. But then we're going to add that much, right? So if we know what X is, we know the solubility of the silver phosphate. And that makes this one 3X. Okay? So our value is 1.8 times 10 to the minus 18. 1.8 times 10 to the minus,
Give us that, okay?
right here.
Yeah, like they have to.
Oh, yes. They either give you that, or if they give you the solubility, you can calculate the K value. You can go backwards and forwards. Here we're going from the K to solubility. We're going to take solubility and go back in the other direction in a minute. So the product here is going to be 3X to the 3rd power and X to the 1st power. Okay? So what does that mean? Well, 3 to the 3rd power is what? 27. And then X to the 3rd power and X to the 1st power is X to the 4th power. Okay? So we just divide both sides through by 27.
On the 4th root of 1.8 times 10 to the negative 18.
So 1.8, 18, and then we're going to divide by 27, and that gives us 6.667 times 10 to the minus 20 equals X to the 4th power. And then we just need to take the 4th root of both sides.
1.607.
Let me see.
Times 10 to the negative fifth.
I gotta find out where my roots are. This is not my usual calculator. Here it is. I think I'm gonna have to use, oh, there it is. Good.
All right, so that was 6.667 times 10 to the negative 20, right?
So 1.61 times 10 to the minus 5 equals X molar.
Okay, I have no idea how you do that, X to the 4. How do you-
Fourth root.
Yeah, how do you do that?
Some calculators have a root function on them. Let me see if yours does.
Is that one?
Yes.
So if I have that number already, can I press that? Is that right?
No.
No. It's not right.
So
I wonder if you could say 4 second that.
C16 is the fourth root.
Would you say that? Let me just plug it in and see what happens. Just see if it comes up correctly. Second to the negative 12. Just see if I get the right answer. Yeah.
I got 1 point. Well, you still got 10 minus 20.
But
Used to be 10 minus 5.
1.6 is correct.
You got that part right.
Why did the,
It must not have been included in underneath the caret. Yeah, it's got to be. If we're going to do this one, we've got to do that. The whole thing has to be under here.
right? Well, I'll put it in again and see.
But that's how you get the solubility. You've got to have the stoichiometry right. And then, how do you choose your X? Choose your X, if possible, so that it's 1 to 1. That way, when you get X, you got the answer.
How did you get the 1.61 again?
How did I get this?
Yeah.
I took the fourth root of this right here.
Okay. No, I put it in, I still got to the negative 20. It got the right number, 1.61, but the exponent is not correct.
You can, all right. If you can't figure it out, you know you can get this part right. Then you just take the fourth root of negative 20, 10 to the negative 20, which is 20 divided by 4 is minus 5. That's the fourth root of 10 to the minus 20.
So just,
Okay, so that's,
hey, FYI, I just discovered this morning that the appendices in our chemistry textbook have a bunch of math lessons.
math lessons?
Yeah, like logarithms were back there and
Oh, okay,
some basic math stuff.
okay. I haven't looked there in a while.
Well, I just discovered it myself this morning, so. In case anyone else finds this as painful as I do.
The biggest issue I had this morning at 3:30 was that I thought I needed log and anti-log, so I kept doing anti-log, and I was not getting the right answer. And it turns out it's just you take log and then do the anchor with it. That was fun. Because I did like
No,
5 problems, and I was like,
Wait, anti-logs only means take it to the other side of the equation.
yeah,
Correct.
anti-log is like when you log on a calculator, it's just like shift and then log. It's like the opposite of log.
So how does, here we're going to introduce the reintroduce the concept of common ion effect. Whereas if you have a solution, or I don't know, maybe we haven't done it before, if you have a solution that's already got one of your ions in it, how does it affect the solubility of your solid? Okay, so in this case, we're saying that silver chloride has a certain solubility in water, and we've determined that. Then you compare that to silver chloride in acidic solution made by adding nitric acid to the solution. Okay. Nitric acid has no common ion with silver chloride. It has no effect on the solubility. Right? That's what we're saying. This is our solubility product, and there are no ions here in common with that, so it has no Le Chatelier effect on the equilibrium. There are no common ions. Okay? If we had used silver chloride, like we did in our lab, then chloride is a common ion, and it would have an influence on that. In fact, if you already have chloride ions in solution and you try to dissolve silver chloride, you're going to get less in solution.
Because the HCl is taking that fluid.
The chloride is there, right? You've already got some chloride there. So the shift is going to be less toward the introduction of more chlorides.
It's like it's adding a little product, so it's pushing it to a reaction.
Right. How about silver phosphate in water? If we acidify the solution with nitric acid. Now, here's the solubility of silver phosphate. We've written that one before.
In the last lab, silver will combine with
That's the second half of our lecture.
fantastic.
So if we combine these two, we put them both in solution, then what do we get? Silver phosphate, nitric acid, and then they dissolve. There's your hydrogen, there's your silver, there's your nitrate, there's your phosphate. So what does that say? It bugs me that these things don't come out as double-barred arrows.
Oh, is that what that's supposed to be?
Yes, it's supposed to be a
Oh,
little.
it's correct on our paper here, though.
Good. Good. I'm glad that's true.
Okay, so that first line under the,
This is the addition of these two reactions.
that's everything.
Yes. Then you look at what combinations can we have. Well, it turns out that PO3 minus is a strong base. In other words, it latches onto hydrogens pretty strong. And when we looked at the dissociation of phosphoric acid stepwise, it turns out that HPO4 2 minus is a very weak acid, which means it makes a strong conjugate base. And there's your conjugate base for this acid. So it's going to latch on to that hydrogen and form this product. So what does that do to the overall? Well, what it does is it removes phosphate from solution. So if it removes phosphate from solution, it wants to drive the reaction toward products. Right. So that's going to make silver phosphate more soluble.
So you could use that to separate silver from something.
Well, at this point, it just means that you can put more silver phosphate in the solution. Right.
By adding another acid.
By adding an acid, any kind of acid. The reason being that we're not focused on the nitrate now. We're focused on the protons. And the proton is the one that unbalances,
And
that disturbs the equilibrium.
most acids have oxygen.
A lot of them do, but not all of them.
Not all of them, but in this case, what is the word for it? Oxyacid.
Oxyacid,
So
nitrates, sulfates, sulfites, phosphates. chlorates, chlorides, hypochlorites, perchlorates. Those are all oxyacids.
So that extra acid helps separate more silver.
It puts more of this in solution simply because we are removing that from solution by combination with the acid, with the proton. Okay, and that Le Chatelier's, when we do that, it goes this direction.
So that phosphate, the PO4,
Mm-hmm.
I guess it's just, how do you know that, like, if I'm looking at it and I see that silver phosphate, how do I just know that that phosphate would desperately rather cling on to a hydrogen proton than a silver? Like, how do we know that?
From our chapter 14 discussion of acids, polyprotic acids. The first dissociation constant for a polyprotic acid is the highest, is the biggest. And they become preacidated less as you remove one more hydrogen. So that means by the time we get down to this one, here it is. That's a weak acid to begin with. But it produces this and this, 1 minus. And then this dissociates into that and that. And then this dissociates into this. Okay? So the K value here, K value here, K value here, increases. This is the smallest one. Small K value means weaker acid. Okay? A weak acid makes a strong conjugate base. So that means when we go from this one to this one, that's the acid, this is the conjugate base. Since K is the smallest of all for this one, that means this is the strongest conjugate base of all of them. And it's going to be attracted to protons more strongly than any of these other anions.
I remember you going over that, I guess I just don't. Just trying to understand the Greek, that's all.
So, wait a minute.
So by saying it's a strong base, I mean, I guess chemicals, it's like they want to achieve some kind of balance or equilibrium. So when it's a really strong base, it just has this stronger affinity for the protons.
Exactly.
It's just like, hey, I'm really negative over here. Somebody bring me some positivity into my life.
Yeah.
Like it's seeking that out, basically. Like, and not just in like a laboratory setting, but like in nature setting.
This is real world.
Like these bases, things want to be neutral. They want to achieve some sort of balanced state.
You can say that about water too, because the equilibrium K value, KEQ, for water, right, actually KW is a special term, is 10 to the minus 14th, which means it's extremely weak acid, which means OH minus is a very strong conjugate base. So if there are any protons around, OH minus is going to snatch them, unless this one is a stronger. And I don't know, I don't have the numbers, can't remember them, but it's very likely that this one is even a stronger base than OH minus.
I mean, would you say like it's pretty relative to that electron charge, like that it's 3 minus, and is that a good just cue, like, hey, we need to see something that?
I don't know if I'd make that jump just yet. I'd stay focused on the quantitative nature. Yeah, this one is bigger than that. This one.
Right, it's a smaller number, right?
Yeah, we're increasing to that point. So this is actually smaller than. So this is 3, 2, 1. So K1 is greater than K2, greater than K3. I'm sorry?
I was just asking if this was helpful to them, but they're
Okay.
like in another world.
Okay, calculate the solubility of silver chloride in first scenario, 100 milliliters of 4 times 10 to the minus third molar calcium chloride. Okay, right off the bat, you can see that we've got a solution in which we've introduced chloride ions. So intuitively, it should tell you that solubility is going to be less because we've already got some chloride there. Common ion effect. Okay. So if we set up our ice table, which only requires that we have the ions, then we say our initial situation is we had no silver, right? We're starting with this much chloride, right? Because calcium chloride makes 2 chlorines. So you have a 2 times that concentration. Okay? So that tells you that if you have this concentration of calcium chloride, 4 times 10 to the minus third, you're going to have twice that much chlorine. That's why the 2. So that's your starting position. This is the chloride concentration before we get any dissolution of silver chloride. Right? We are going to get some dissolution of silver chloride. Why? Because there's
water, all of this in water?
Yes, well, this is all aqueous, right? We are going to get some dissolution of silver because there's none to start with. And Le Chatelier says it's got to go that direction. We're going to get some dissolution of silver chloride because there's none of this here. So we're going to get some of that, 1 to 1. So we're going to have X there, X there. And X again, since it's 1 to 1, references the solubility of silver chloride. So at equilibrium, we have X silver and 8 times 10 to the minus third plus X chloride. Right? So the solubility product is still valid. It's just that the solubility position is different. Right? We're looking for the solubility, the position, not the K. We know the K. So if we plug these values in, they're equal to the K value. We're going to say X is so small that we can ignore that one. And then solve for X, and we get 2 times 10 to the minus third molar, 10 minus 8 molar. So what was it before without? Well, is it going to tell us? I probably stuck that in there, didn't I? Right? 100 milliliters doesn't matter. Okay.
So
It was 10 to the minus fifth. Okay. 10 to the minus fifth was our solubility without the common ion at that concentration, and 10 to the minus 8. So we've lost 3 orders of magnitude solubility simply by adding some chloride ion.
So That constant KSP up there, that was for the silver chloride.
Yes, silver chloride.
Why doesn't it matter how much there was? I mean, just
Because it's an aqueous solution, and the dominant molecule is water. So we've actually got two solubilities competing with one another. It's this original solubility, which is virtually 100%, and then the solubility of the silver chloride.
so that number we solved for down there, that X, is just saying that if you have an aqueous solution that already has calcium chloride in it and you throw in some silver chloride, that is going to be the final concentration of the silver chloride?
Yes, solubility of silver chloride. Well, this is going to be the solubility of the silver chloride. Now, if you want to know the concentrations, this is the concentration of silver ions. But the concentration of the chloride ions would be the summation of this one and that one.
Okay, so I guess I'm still a little confused by that. I see what you're saying. Okay, so that the concentration, the 2.0 times 10 to the negative 8 molar, that's the concentration of silver ions. That's the concentration of chloride. But then what, how is that number the same as what the solubility for silver chloride in calcium chloride is?
Yes, that is the solubility in this concentration of calcium chloride. If we change the concentration of calcium chloride, that will change too.
I guess I'm trying to understand how those numbers all relate. The fact that we're using the molar, that molar number to represent this other concept.
Okay,
Is a little confuddling
Yeah.
to me.
we're talking here about an equilibrium position. And it settles at this point simply because of that. But the solubility itself of the silver chloride is dictated by this.
I guess I need to think about it like that. It's an equilibrium position.
Right. Is it the equilibrium constant, or is it the equilibrium position? So what would the effect of calcium nitrate be? Nothing. There's no common ion. Solubility would be exactly the same as in water. Okay. So now the topic becomes, rather than solubilizing a solid in aqueous solution, at what concentration of ions in solution will you get a precipitation? In other words, will the process reverse? Okay. And to know that, we need to compare the solubility product with the Q value. We've done Q's before. You just do calculate your Q the same way you do the K, only with the given concentrations of the ion pairs. So if Q is greater than KSP, you're going to get a precipitation. If Q is less than KSP, your solution is not saturated. It has to exceed KSP before you will get precipitation.
And if Q is equal to KSP?
Mathematically. But physically it's not, because Q is not equilibrium. K is equilibrium, Q is not.
So it doesn't mean anything if they are equal?
Oh, if they're equal?
Yeah.
That means the solution is saturated.
It's just saturation.
Yes, yes. So how do we use this information? Well, if you have a mixture of cations and you want to separate them, then all you need to do is pick an anion that will combine with, it can combine with both of them to produce a precipitate. But the KSP has to be several orders of magnitude different to get an efficient separation. In other words, in this case, we're talking about barium and silver in solution. So what would happen if you add sodium chloride? Well, it forms a precipitate with silver chloride, but chloride and barium are soluble. Right? That's the simplest way. We know that this one is insoluble, silver chloride, relatively speaking. Right? That's very low solubility. But barium chloride is very high solubility. It's virtually 100% soluble. So if you just have those two ions in solution, you add sodium chloride to it, then the chloride reacts with the silver, precipitates it, and leaves barium behind. And you've got a separation. Then you just need to filter them. Okay? That's the simplest form of separations by or selective precipitation. It can get a lot more complicated than that.
So, do most salts have that reaction with metals?
There's usually, yes. Well, to broadly answer your question, most metals do have such different solubilities with various anions that you can separate them. You just have to pick your reagents correctly and use them in the proper order. That's two things. You need to have the right reagents and use them in the proper order to effectively separate cations that are mixed in solution.
Kind of like we did with the iron thiocyanate, like that whole cycle we took to get back.
I guess there are some similarities.
But I mean, is that kind of the process of thinking like you have those chemical steps to separate?
Yes, yes. Yeah, you could say that. So the previous slide had separation based on chloride solubility. This one is based on sulfide solubility. So if we want to separate these two from these using hydrogen sulfide, then at low pH, the concentration of sulfide is relatively low. Which means if you keep this low, then only the very insoluble sulfides will come out of solution, like mercury and copper. They have very low solubility products with sulfide. So we want to keep the sulfide concentration low so that it doesn't precipitate these. Their solubility products are higher than the sulfides for those. So we use an acidic solution, which means that the concentration is low here. Then, once we get those out of solution, then we can add a base. That puts more of this in solution, and now we can precipitate out the manganese and the nickel. Now, I'm not going to have you memorize all these. In fact, you're going to have the charts available. Just know how to use the charts.
Was that an example of like just wanting to do them in a certain order?
I'm sorry?
Was that supposed to be an example of like wanting to do the mercury and the copper like first for some reason, like just to
Yes.
do them in a certain order?
Right, the order matters, correct.
And why was that? I mean, what was the case for that?
Oh, we're trying to separate cations from a more complex mixture. The first one was very simple, barium and silver, to give you the kind of a step up, small step up into what we're trying to do using precipitation to separate. And then this gets a little bit more complicated. So we use hydrogen sulfide at low pH to differentiate, separate these two from those two. Then we add base, which makes more sulfide available, which now we can precipitate manganese and nickel.
As sulfides.
Yes. So what we're doing here is the Q value here, we want it to be just barely above the K for these two solids. Then we're going to change the Q value by changing the pH. We're going to change the Q value now to a higher value. And remember, if Q is higher than K, then you get a precipitation. But for these two, at this stage, Q is greater than K for these, but Q is less than K for these. So then we change the pH, and that changes the Q. The Q now becomes much greater than the K's for these, and they precipitate.
So was this assuming like the copper, mercury, nickel, and manganese were just like in their pure state in solution?
Oh, they're ions in solution, right? They don't have to be very high concentrations, right? They're
So
just,
what happens if you do the base first?
then you get all of them out of solution at once, and you just get the mix. You get all of these as sulfides down here. Those, you're still mixed together. You don't separate them. Because if you do it basic, then the Q is greater than both this set and that set. And you precipitate everything at once. And that kind of defeats your purpose. You want to do some separation. So you control the Q to be greater than this one, but less than this one. Get these out of solution, then change the pH, which also changes the Q. Now this is what a selective precipitation looks like if you have this mix of cations. We've got lots of cations here. And this is typically what you would do. Add hydrochloric acid. That takes out silver, mercury 1, mercury 1, and lead 2. That's group 1. This is group 1. Then you would add the hydrogen sulfide in acidic solution, and that removes, our previous example was copper and mercury too, right? But it will also remove bismuth, cadmium, lead, arsenic, antimony, and tin.
So we're using acids to filter water, basically, of their metals, the metal.
Say that again?
We're using acids to filter metals out of water.
In this case, yes.
Precipitate them, and like you could then filter it out.
Right. You're making the solution acidic. Then after you filter these out, it's still acidic. But we're going to add hydrogen sulfide, right? So we know that acidic hydrogen sulfide will only precipitate out. Well, our previous example was this one and that one, but it'll also take out these. Then we neutralize the acid, make it basic. And now we'll take out these. Let's see. Hold on a second. Yeah. Okay, in this case, the group 3s are a combination. We're going to take out these sulfides, plus these hydroxides, because we also added hydroxide in that process. So aluminum, iron, chromium hydroxide will drop out of solution along with zinc, nickel, cobalt, manganese, and iron. Then to finish it off, group 4 we'll take out by adding sodium carbonate. And that will get us barium, calcium, and magnesium carbonate. Because none of these processes will take these out as carbonates. I think there's probably...
Sodium carbonate base.
It's basic, yes.
Salt. Salt.
Yes, when you dissolve sodium carbonate in solution, it produces a basic solution. Remember our rule of thumb? Sodium is from a strong base, carbonate's from a weak acid, so the result is a basic solution.
So many thumbs to remember. So many rules of thumb.
Don't have enough thumbs to go around.
Yeah, no.
Okay. So you don't have to memorize those. Just learn how to use the chart. So what steps do we go through to get down to here? If you like run into a question on the exam that says, you have a mixture of group 2 through 5, how do you separate out the group 2s? Well, you just add hydrogen sulfide in basic solution and bam, that's what you get. Just learn how to read the chart. Okay, now let's get to complex ions before we run out of time. We have to get this lab done today. Complex ion equilibria. The thing about complex ion equilibria is the complex ion does form in solution, but it stays in solution just like the ligand that it comes from, right? So what's a ligand? Well, a ligand is a metal. No, I'm sorry, I got that backwards. Not the ligand. The ligand is what attaches to the metal. In the case of ammonia and silver, silver is the metal, ammonium is the ligand. Okay. And we have a K that can be associated with it. And it's often given the, let's see, it can be an F or it can be an S or an ST for stability, formation constant. So in that case, let's see. Do I have to write it or is it going to pop up there for me? Yeah, not the one I'm thinking of. So let's say we have, we've got this one, right? And it does that if it's just aqueous solution. But if we introduce this one in that solution. Oh, no, I'm sorry. That's not right. We have a solution that's made up of this. Okay, so these are aqueous. Aqueous. This is aqueous. I don't remember the equilibrium constant right now. It's actually in your, well, it's not this one, it's the next lab. The equilibrium for this one is way over here. Mostly ammonia, right? Not ammonium. And this ammonia will combine with that silver. It is a ligand. So we get one of these plus one of these, and it forms this still has its charge in solution, but it doesn't stop there. It takes this one and adds another one. There. Now it stops. That's as far as it goes. So the overall reaction is to combine silver ions with ammonia and make two ammonias and make this. Right? So it's kind of like, remember, acid dissociation constant is one proton at a time. Each one of these steps has a K. So this one will have a K, and this one will have a K. And you just write this one divided by that one times that one is your K. So we would write, this is our complex ion. Like that.
Where'd the other ammonia molecule come from?
This one?
Yeah.
From here. We got lots of them. So overall, we could write another K, right, for the second one, and that would be that one. Actually, there are two of them, like that. And then here, we would have this one. And
NH3.
yes. There. So you have these two. So each step, like this step, and then this step. And then you can get a K for the overall reaction. Just use your Hess's law and combine them. And of course, when you combine equations, what happens to the K values? Multiply them. So if you combine these two, then your overall K would be this one times that one. And you would end up with let's see. Starting out with these. We're going to have two of these. And then this one, that one. There. So that would be the combined K. Stability constant.
Are we gonna have to calculate that?
A
A combined thing like that?
Possibly. But I'm going to give you, next week, for the week after, I'm going to give you the lab exercise for the one where we actually do this in the lab. Okay? And it's got all those calculations in it. Okay, we're about out of time. 45. Oh, we're way past. Right?
45.
Yeah, we're 15 minutes past.
All right. Well,
So the rest of this is calculations of, oh, okay, so I do have a slide on that. There is a slide on those calculations, the last set of slides. So this shows you a sequence, just like the silver, only this one goes through 4 iterations. Right. So if the anion of the solid is a good base, the solubility can be greatly increased by acidifying the solution, just like our phosphate. You acidify it, the conjugate base picks up a proton and drives the reaction that way. If the anion is not basic, if it becomes a competitor, then very often choosing the right ligand can solubilize it. And that's what we're going to do with silver in 2 weeks.
Is this a long line?
Not supposed to be.
Maybe you can help us speed things along.
Oh yeah, I think we can get it done. We only need to go through it once to get the data, because we're just going to draw a titration curve and use that information to determine the KEQ for acetic acid.
So it's just deceptively long, because this is all extra information.
Yes.
Probably help us while making the lab work.
I would hope so, yeah.
Also, you said this was informal, correct?
Not this one.
This one.
Oh, that one, yes, yes.
Okay, that's good.
Le Chatelier's is informal.
Good.